To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
So my dear children, in the earlier chapters, we discussed several things regarding the nanotechnology lesson part. Over there, we discussed about the definition for the nanotechnology. I mean, like we have discussed what does the nanotechnology is, and we discussed about the history related to the nanotechnology, and we discussed even some examples, natural examples for the nanotechnological materials. Okay. Nature-made nanotechnological materials. Also over there we discuss about the Lotus effect, and when you take a human and animal cells and also in plant cells, the organelle levels, right? We discuss about those things in the previous chapters. Now it's time to discuss like what is the specialty in the nanoscale? Why does the nanoscale matters this most? So we'll be discussing this one within the next part, my dear children, which is given over here. Why nano size matters? Why nano size matters? Okay, so here it is given, substances behave differently in the world of atoms and molecules. Both physical and chemical properties of matter substantially change when the size reaches 100 nanometers or below, although it is the same bulk material. Now the specialty here is that, my dear children, when you take a certain material, okay, when you take a certain material, even though when it is observed from the outer side, if you can observe it as a macro element or macro substance, right, even though you can observe it as a white color nature in the outside, when you go to the nanoscale of it, okay, when you go to the nanoscale of it, their properties is going to differ from 100%. I mean, like if the outer structure is like in white color in nature, when you go to like 1 to 100 nanometer in scale, here the structure is getting changed into a different color. Totally different color can be observed. Like that way, physical and chemical features are also going to differ when, right, even in the same material but in the nanoscale, right? Even though those things are in the same material, even though that is the same material, when you go to the nanoscale, right, the world of nanoscale is way more different than what you observe, right? So macro world and nano world are two different things. The properties that can be observed within the macro world cannot be observed at the micro or else at the nano world, my dear children, right? The properties are going to change. I mean, like there's vast change in the properties, right? Properties are heavily going to change. So this is the case, or this is the issue in here, or else this is the specialty in nanoscale, my dear children. Okay, so physical properties such as optical, mechanical, electrical and magnetic properties changes at the nanoscale, while chemical reactivity significantly change. So chemical reactivity means ability of bonding with other materials, my dear children, right? That means ability of making compounds, right? In simple, that is what do you mean by the reactivity. So this ability of making different kinds of compounds and substances, right, significantly going to change when they are going to reach to the nanoscale. So nanomaterials, nanoparticles are much reactive than macroparticles, very more reactive. Okay, so there are several changes that is going to happen. I mean, like there are several changes which is going to happen, physical changes which is going to happen because of the nanomaterials or because of the nanoscale. However, Upon change in the physical structures, my dear children, right, their chemical reactivity doesn't remain the same, but their chemical reactivity is also going to change, dramatically change, right? So drastically their reactivity is going to change when these particles are reached into the nanoscale. Okay, so given metal copper example for that thing. Okay, now I told you that physical and chemical properties are going to change now. So let's see an example. See, metal copper is transparent on the nanoscale, while gold demonstrates a range of colors depending on the size and shape at the nanoscales. Chemically inert gold become highly reactive at the sizes below 100 nanometers. Now, metal copper is transparent on the nanoscale. Here you can observe the normal nature of copper, right, in macro scale and in nanoscale. Can you see there is a like transparent nature? Light blue color transparent nature can be observed in the nanoscale of copper particles, but in here you can observe copper at a different, right, color. Copper related color can be observed over there. However, in here, right, you can observe some kind of a transparent nature. It's because that when copper is going to change into the nanoscale, right, the color is going to change. Okay, color is going to change. The other thing is that, my dear children, the color of gold. Okay, the color of gold. So color of gold can be observed, right, according to the size in, right, as per to different colors. So here you are given with the nanoparticles of gold and how the color is getting varied. So various colors are observed in gold nanoparticles when the size of particles are below 100 nanometers. So when the size of the particle reach below 100 nanometers, we can observe different colors in gold like this. Okay. So not only that, my dear children, when you go for the chemical reactivity, chemically inert gold, what do you mean by inert? Now inert means, my dear children, when you take a certain substance, if it is not that much reactive, then that particular substance is referred as an inert substance. For a certain example, gold. Gold is an inert substance. Why I am saying that? It's because that, my dear children, gold, when you take gold, gold has, right, gold has a certain ability. Okay, gold has unique property like the glitterness, okay, or the metallic luster. So the luster of gold is not going to fade away even longer time is going to pass by. I mean, like, even though it is taking several years, the lustrous nature of the gold is not getting faded away that much quickly. It's because, my dear children, when you take gold, okay, when you take gold, gold has some kind of an inert nature when this gold is in macro scale. Okay, when the gold is in macro scale, it has some kind of a unique inert nature. Inert means not that much chemically active. Okay, that is why actually the glitterous nature of the gold is not getting faded even though the time is going to pass in longer years, right? I mean, like, when you take another material, right, especially when you take metal like iron is going to rust very quickly if it is exposed to the normal environmental conditions, but gold is not like that. It's not going to rust or tarnish even though time is going to pass by. So, my dear children, even though the gold has a glitterous nature, right, when you compare gold with the iron, even though gold has the glitterous nature, it's because that the gold is, my dear children, somewhat way more less reactive than the iron. Now I told you that iron is going to tarnish. right? Iron is going to tarnish, or that tarnishing process of iron is specially called as rusting. Iron is going to rust when the time is going to pass by. Okay, when the time is going to pass by, iron is going to rust very quickly. So this rusting nature is because of the reactivity. This rusting nature can be observed because of the reactivity. Because of the reactivity, iron is going to rust quickly. So upon rusting, that glichrous nature or the luster of iron is getting reduced. But the luster of gold is remained for a longer time period because of the less reactivity. Okay, because of the less reactivity. So less reactive gold, my dear children, okay, less reactive gold is more highly reactive at the 100 below at 100 nanometer level or below 100 nanometer level, my dear children, right? So this is the specialty in the nanoscale. Their physical property is going to change, and also the chemical reactivity. Chemical reactivity is dramatically getting changed when reach into the nanoscale. Okay, even the gold, which is an inert substance in the nature, when in our macro world, is getting into a very highly reactive substance when going into the nanoscale. Okay, this is the specialty. Right then. Number 2 given, carbon can be converted into resistance-free conducting materials at nano level. Strength of carbon nanomaterials could be several times higher than steel. So the next one is carbon nanomaterials, carbon-based nanomaterials. So you are given with several figures related to carbon-based nanomaterials, my dear children, right? Like the fluorine, diamond, right? Then carbon nanotubes, graphite, graphene, like that way you can observe several structures related to carbon. All of these structures, my dear children, are carbon nanomaterials. That means each of this dot is going to show, right, is showing one single carbon atom. Okay. So carbon can be converted into resistance-free conducting material at nano level. Strength of carbon nanomaterials could be several times higher than steel. So my dear children, this is the second important fact. Second important fact is that, my dear children, here when you take carbon nanomaterials are way more, right? These things are way more, right? Strength, they have a way more strength when going into the nanoscale. Their strength is very high when you are going into the nanoscale. I'm talking just only with the nanoscale. Okay, my dear children, that means my idea is the bond between two carbon atoms. Okay, two or more carbon atoms. These particular lines which are shown by, right, structures, these lines, I'm talking about that strength. Okay, strength about those bonds. So these bonds are very stronger. Okay, so strength of these carbon substances, carbon-based nanomaterials, are very high. And the other thing is that, my dear children, carbon can be converted into resistance-free conducting materials. What do you mean by that? When you take electricity, there are certain factors related to the electricity. There are several physical factors related to the electricity. One physical factor related to the electricity is voltage. That's the potential difference. When you take the positive and negative terminals of a certain, dry cell or else any kind of a electric source, when you take the positive and negative terminal, the difference between the charges of positive and negative terminals is referred to as the potential difference. Potential difference. So potential difference is going to change, right? Potential difference is going to change from one electric source to another. Then another factor is that, my dear children, the current which is going to flow. So according to the potential difference, the current is also getting changed. But however, mainly we can observe when you take an electric source, we can observe these two factors. When you take a conductor, certain conductor, electrical conductor, an electrical conductor is carrying certain amount of electric current from one terminal to another. So in here, there is another factor related to an electrical conductor which is going to give out an opposite force for the flow of electrical charges. In simple, for the flow of electric current. This particular one is referred to as the resistance. Right? This factor is the one which is referred as the resistance. Electrical resistance. So electrical resistance, my dear children, right? Electrical resistance is giving out an opposite force or else an opposite obstacle for the flow of electrical charges, right? For the flow of electrical charges. That means obstacle given against the flow of electric current is referred to as the resistance of a certain conductor. So higher the resistance, less amount of electric current is going to flow through the material. When the resistance is very high, right? When the resistance is very high, what will happen? Very less amount of electrical charges is going to flow from the material. Less amount of electrical charges or else less amount of current is going to flow through a material when, right? When there is high amount of resistance. If the resistance is low, then my dear children, if we are going to provide 1 ampere of a current, then from the other side also we can receive the same amount of current. That means the efficiency is very high. Efficiency of flowing current is going to be very high within a conductor if the resistance is less. Then when you take a certain material, macro element, or else a macro conductor, any conductor in our normal environment, each and every conductor has some amount of electric resistance. Now you know that our conducting wires in our normal day-to-day life, our conducting wires are mainly made up of copper, right? However, if you can replace copper with silver, you know that usually metals are the ones which are behaving as conductors. Electrical conductors are metals. So metals are the ones which are behaving as electrical conductors. So metals are electrical conductors because they have free moving electrons. I think you could remember we have learned this thing within the, when we are discussing about that chemical reactions related to electricity. Over there we discuss about that thing. What is that lesson part? It's the lesson which we discussed about the electroplating process, right? I think you can remember about that thing. So during that time, during that lesson, my dear children, okay, I told you about the free moving electrons that the metals have. Okay. So specialty here is that, my dear children, when you take a certain metal, they have free moving electrons. Even though they have free moving electrons, because of the resistance, right, some amount of electric current is getting, because of the opposite force given for the flow of electrical charges, some amount of electric current is, right, some amount of electric current is getting wasted when flowing electricity from one place to another through a normal conductor in our environment. Each and every conductor, even the copper, has that feature. I told you that usually we use copper as our main electrical conductor. So conducting wires are usually made up with copper. If you can replace copper with silver, then, my dear children, you can save a lot of money. Why is that? Because the resistance in silver is very low than the copper. So you can save plenty of electricity. And also, if you can replace your copper, right, if you can replace your copper conducting wires with silver, then half of your electricity bill can be saved for sure. Nearly half. Because large amount of electricity is getting wasted because of the resistance, right? Because of the resistance, large amount of electricity is getting wasted. However, my dear children, each and every conducting material in our environment, it has some amount of resistance. Some amount of resistance. That means each and every conductor, okay, that means each and every conductor, my dear children, each and every conductor, right, when the current is going to pass by, within each and every conductor there is a small bit of a loss of electric current because of the resistance. But the specialty in carbon nanoparticles is that when you take the carbon nanoparticles, you know that usually carbon, like graphite, is going to conduct electricity. In macro scale, they also have some amount of resistance. But when you go to the nano scale, my dear children, the resistance is going to be free. Right? These particles are resistance free. That means, my dear children, the obstacle given out for the flow of electrical charges is nil, zero. Okay? Means that, okay, we can save like huge amount of money. A large amount of wastage can be minimized because of using these conductors. These things are also referred to as superconductors. Superconductors, right? That means the resistivity of these materials is going to be zero. So the resistance is also zero. Okay, right? So these materials, carbon nanomaterials, can be used to create what? Can be used to create conductors that are resistance free. Okay, and also the strength of these particles are also very high, right? So there are several structures, as you can see here within the figures, my dear children. There are several structures related to the nanomaterials of carbon, my dear children. So when you go further with the lesson, you'll be learning about these structures, right? So just for now, you just look at the figures and get some idea about the carbon nanoparticles. Right then. Then the next topic given, surface area of nanoparticles. The surface area of the nanoparticles. Okay. Main reason for such changes in physical and chemical properties is the increase in the surface area to volume ratio, A to B ratio, when particle size decreases. So my dear children, now this is a very special part. Very special. What is that? Here it is given, the main reason for such changes in physical and chemical properties, the main change because of the change in size, is because of the change of A to V ratio. What is A to V ratio? A means the surface area, V means the volume. Okay. So because of change in the surface area to volume ratio in substances, the reactivity of the substances is going to change. Reactivity is going to change. Reactivity is dramatically changing in here. So, as an example, let us consider a 1 centimeter length cube made of silver. Volume of the cube is 1 cubic centimeter and the surface area will be 6 square centimeters. This 6 square centimeter area is equal to surface area of a stick gum. That means chewing gum, right? So, as an example, consider 1 centimeter length cube made up of silver. The volume of the cube is 1 cubic centimeter and the surface area will be 6 square centimeters. This 6 square centimeter surface area is equal to the surface area of a stick gum, right? That means chewing gum, right? Stick of gum or else chewing gum, the surface area. So we're going to take a cube like this. I'm going to show you how it is going to change in here. Now, when you go to the nanoscale, let's see how does the surface area and the volume is going to change. Volume means the space occupied by a certain substance, no? So my dear children, even though the right, a substance is in different stage. Now let's see like this. I'm going to take a cube, right? One cube or else a cube, right? That has a volume of, I'm going to take a cube that has a volume of 1 square centimeter, right? 1 cubic centimeter, not square, 1 cubic centimeter. So even though I'm going to cut it to several different pieces, the volume occupied by that certain object is not going to change. Volume means the space occupied by certain object, right? Volume means the space. So space occupied by a certain object is not going to change even though I'm going to cut it into several pieces, right? The volume, total volume is not going to change. For simple idea, let's take like this. Now there is a certain metal cube. I'm going to melt that metal cube and I'm going to turn it into a different structure. Let's say it is a statue. So if the volume of that particular cube, initial cube was like 70 cubic centimeters, then volume of the statue is also equal to 70 cubic centimeters. Volume of the statue is also 70 cubic centimeters. It's because that the same thing is the same material or the same metal is being molded into a different statue over here. So their volumes are not changed. Volumes are not changed. But the surface area is going to change, my dear children. Okay, how come the surface area is going to change even though the volume is not changing? Let me do you a simple calculation in order to show that. Okay, let's take a cube like this. Okay, this is a cube. Let's imagine that this is a wooden cube. So what I'm going to do is, let me draw this one also. Right. Now let's imagine that length of a side is 2 centimeters in this cube. Okay. Then what I'm going to do is I'm going to separate this cube. Into smaller cubes like this, my dear children. Okay. Like this, I am going to separate this thing into smaller cubes. Like this. Okay. So how many cubes can I remove or else cut by using this larger cube? I'm going to cut this thing into smaller pieces like this. Okay. Side length of this one is 1 centimeter each. So my question is, how much of those smaller cubes can be cut by using this larger cube? To find that one, what do you need to do? You take the volume, the space occupied by this object, and divide it by the space occupied by that object, because when converting this one into that thing, the volume should be equal to each other. So we can identify how much of, right? We can identify how much of cubes can be cut by using this particular object. Okay, by using this particular object, how much of cubes can be cut? to have this kind of dimensions. So here the volume is very simple, 2 times 2 times 2. So 2 to the power 3, 8 cubic centimeters. Here the volume is 1 times 1 times 1, 1 cubic centimeters. So when you divide 8 by 1, my dear children, you can cut 8 pieces. So there are like 8 pieces of these smaller, right? These smaller, wooden boxes, right? There are 8 pieces of these wooden boxes which can be cut by using this particular larger wooden box. Okay, right then. So my dear children, now let's see the surface area. Surface area means area of this surface. Now there are 6 surfaces in this object or in this cube. So to find out the total surface area, what you have to do? You just take the area of one certain surface. So the surface which I have colored over here has an area of 2 times 2. Area means, my dear children, length into breadth, no? So length 2, breadth 2, 2 times 2, 4 square centimeters. So area of this particular surface is 4 square centimeters. Like that way, there are 6 such surfaces. So the total surface area of this particular cube is equal to 4 square centimeters into 6, as there are 6 sides. Altogether 24 square centimeters. 24 square centimeters. Where when you cut this particular object into 8 pieces to have 1 centimeter a side length, actually that means here 2, here 1, that means like half, right? I'm going to cut this particular object into these particular objects. So over there, the length of a side is exactly half of this one. See, you can observe it very clearly. Even though their sizes are getting reduced, you can observe that the volumes are same. Means that here 1 cubic centimeter, so that I can cut 8 of them. So 8 into 1, 8 cubic centimeters is the volume of these 8 pieces. And also here the volume is same thing, 8. There is no change in the volume. Now let's find out the surface area of that smaller 8 parts. Okay, let's see. So here total surface area. First of all, let's take the surface area of this particular cube, not the surface, cube. So to get that one, I'm going to take the surface area of this surface. It is equal to 1 times 1, 1 square centimeter. So like that way, within a cube, there are 6 surfaces. So cube's area is equal to 1 times 6 square centimeters. That means one particular cube, just one particular cube has 6 square centimeters. Why is that? Why it is becoming 6? Because, my dear children, one surface area of one particular surface is equal to 1 times 1 square centimeter. Like that, there are 6 sides. 1, 2, 3, 4, 5 and 6. In the same way like this, one particular surface has 2 times 2, 4 square centimeters. Like that way, there are 1, 2, 3, 4, 5, 6. Altogether 24 there. So in here, smaller ones, once again there are 6 sides. However, the area is 6. Right? Area is not 6. Area is 1. There are 6 sides. So altogether total cube's area becomes 6 square centimeters. How many cubes are there? 8 cubes are there. So our answer becomes 8 cubes. See, 8 cubes into 6 square centimeters. Altogether 48 square centimeters, my dear children. See how the area is getting changed. Even the same material is being cut into pieces. This is the same material, my dear children. The same object. Even though I am going to separate into smaller objects, the same material, volume unchanged. But the surface area, the contact area is going to change from one single value to twice of it. So what will happen if you cut even more? What will happen if you cut even more? Even more. Up to the nanoscale. Now you are going to take this object and you are going to cut it into nanoscale. That means to have a cube that has a 1 nanometer of a length. And you are going to cut this particular object. Then, my dear children, the surface area of those particles going to be like million trillion times like this. That's why in the nanoscale, the properties are going to change heavily. Properties are dramatically changing, especially the reactivity. So when the surface area is going to increase, my dear children, the reactivity is going to be very high. Let me give you a very simple example for this. You take a large wooden log and try to burn it. Will you be able to burn it quickly? Of course not. If it is a giant wood log, it will take much longer time to burn. Even you won't be able to burn it quickly. Right? You won't be able to burn it quickly. So, my dear children, now take the same wood log and chop it into smaller pieces. If you can make it into sawdust if you want. Even though you are changing that particular wood log into wood pieces or else into sawdust, there is no change in the volume. If you measure the mass of the substance is same. However, now try to burn the sawdust or the chopped wood particles. These things will definitely, like in a flash, like in a sudden, it will react with oxygen and it will combust for sure within very short time period. What is the reason for it? Reason is the surface area, my dear children. When the surface area is high, particles can interact with other particles very quickly. So oxygen, you know that in order to react certain substance, in order to burn certain substance, we need oxygen. So during a combustion, when you take a certain combustion or else when you take a certain burning process over there, oxygen is bonding with the particle or the fuel, right? Oxygen is interacting with the fuel. So in order to have this interaction, or in order to have this interaction, right, the oxygen should have the ability to interact with that particular fuel very quickly. In order to do that, the surface area of the two substances should be high. Okay. If the particular fuel has a higher surface area, then it will burn up very quickly. That is why, my dear children, liquid fuels are getting caught up with fire very quickly rather than the solid ones. Okay. Right. So in the same way, my dear children, even though larger wood logs are taking very long time to burn, however, chopped ones or else sawdust will catch up with fire instantly. It's mainly because of increasing surface area when the particles are going to be smaller. So if you can reach up to the nanoscale, that means, my dear children, here the reactivity is extremely high. Even we won't be able to calculate that thing up to a certain level even you're taking these nanoparticles, or you're going for the nanoscale. So the reactivity is going to be extremely high. This extremely high reactivity is observed because of changing the surface area. The surface area is dramatically changing even though the volume is getting remained at the same value. So this is why the nanoparticles are this much reactive. Okay, right then. So if that volume of 1 cubic centimeter is filled with cubes of 1 millimeter length, that surface area of total cubes will be equal to the surface area of a single page in exercise book. See how does that change is going to happen? Change in the surface area is going to happen. Here it is given. Now in the earlier, can you remember? I'll take the slide somewhat down. See, consider a 1 centimeter length cube made up of silver. The volume of cube is 1 cubic centimeter. Surface area will be 6 square centimeters. This 6 square centimeter surface area is equal to surface area of a stick of gum. That means chewing gum, right? This surface area now is like a chewing gum. 1 centimeter length cube made up with silver. Okay, that means like this kind of a cube. Surface area is like size of a chewing gum. Okay, the same cube, when it is been cut into how much? If the 1 centimeter, right, if 1 centimeter of that cube is been cut into 1 millimeter length cubes, then what will happen? That surface area of total cubes will be equal to the surface area of a single page in exercise book. So that 1 centimeter length of silver, if it is being cut into 1 millimeter size of cubes, then that 1 millimeter size cube, when you consider all of those cubes, the total surface area is enough to fill a book. Okay, not a book, actually page of a book. One single surface of a page of a book. Then when the 1 cubic centimeter of volume is filled with 1 nanometer size cubes, now to the nanoscale. Okay, 1 cubic centimeter volume thing, that means it's like this, right? Like this much. 1 centimeter, no, like this much, right? Somewhat similar to, like, you know, this much. So when you take this much of a cube, and if you can cut that cube into nanometer size smaller cubes, then let's see what is going to happen with the surface area. So when the 1 cubic centimeter volume is filled with 1 nanometer size cubes, that means if you can cut that thing into 1 nanometer size cubes, then the total cubes needed to have a surface area which is about 1/3 of football court. My God, see how does the surface area is going to change? If you can cut the same thing into nanometer length, 1 nanometer length, right, into a 1 nanometer length cubes, then my dear children, right, the specialty here is that the total surface area covered by those cubes is equal to 1/3 of a football court. 1/3 of a football court. Started from a chewing gum, came to a size of an exercise book page, then now we are at the football court, 1/3 of a football court. See the change in surface area. Okay, drastically changing. So when the particle size is getting smaller and smaller, the surface area is dramatically changing, my dear children. So this is the specialty in A to B ratio. However, the volume is constant. Volume is unchanged. right? But the surface area is dramatically changing. So change in surface area is the main reason for this extreme reactivity and the change in different properties related to the physical things. Okay. So nanomaterials, nanoscale materials have far larger surface area than similar masses of large scale materials. As surface area per mass of a material increase, a greater amount of the material can come in contact with the surrounding materials, thus affecting reactivity. So like I said, my dear children, okay, like I said in the previous slide, can you remember? When increasing the surface area, what is going to happen is more and more particles have the ability and to come in contact with these surfaces. So when more and more particles are coming in contact with these surfaces, what will happen? Their interaction ability between surrounding particles is also going to increase. Here, upon increase in that thing, what will happen? Definitely, my dear children, right? Definitely, the reactivity is going to increase. Actually, chemical reactivity is mainly dependent on, hugely dependent on that factor. Which factor? The surface area. Higher the surface area, very high the reactivity. Lower the surface area, lower the reactivity. Okay. Like I said in the previous one, that is why when you take a large wood log, it's not going to react with oxygen or else to combust quickly. But however, if you chop it into pieces, it will react very quickly with oxygen. That means it will combust very quickly. The reason behind this thing is the surface area. Higher the surface area, very high, right? Very high the reactivity of the substance, my dear children. So I hope that you got the idea quite well regarding the A to B ratio and how does the volume is going to be constant while increasing the surface area. Okay, always remember when you go in nanoscale, the surface area is going to change drastically even though the volume of substance is not getting changed. If the volume is not changing, the mass is also not changing. However, the surface area is changing. Okay, so this change in surface area or the increase of surface area is the reason for the higher reactivity, right? So you are given with a figure, right? So by looking at this figure, my dear children, you can get a certain idea. As you can see here, see, this is 1 centimeter length cube cut into several pieces, and when you take a portion of it, the surface area is like this. And when you take the same one and when you cut into even smaller cubes and when you take a piece, so the total surface area is like this, right? So by just looking at these figures, you can get a very clear idea about how does the surface area is going to change when decreasing the size of particles. Okay, as you can see here within the figure, very vast area is going to be covered just by taking a very single portion of this thing. However, these things are being cut into, right, nanoscale particles. So this is the importance in A to V ratio, my dear children. Area to volume, surface area to volume ratio. Okay, so once again here it is given as surface area per mass of a material increase, a greater amount of material can come in contact with the surrounding materials, affecting the reactivity. So large amount will come into contact, therefore the reactivity or the reaction of a certain substance, reactivity ability of the certain substance is going to increase. Okay, so my dear children, I hope that you got the idea about the reactivity of a substance, how does the reactivity is going to change. And my dear children, I hope that you got the idea about A to V ratio, right? This is a simple idea regarding the A to B ratio, my dear children. There are different other things as well we will discussing, but however these things are really basic things. So I hope that you got the idea about the basic things first. Okay, so my dear children, with that part I'm going to finish up this chapter. So within our next chapter, I'm going to discuss further things related to the lesson part. Especially we'll be discussing about different kinds of nanomaterials regarding the carbon based nanomaterials. Okay, we'll be discussing about their special properties, and we'll be discussing about further things related to the lesson part as well. Okay, so within this lesson part we discussed an important factor related to the reactivity of the nanomaterials, and what is the reason for the change in reactivity, and what is the reason for change in physical properties as well. So from that I'm going to finish up this chapter. In our next chapter we'll discuss the further things related to the lesson.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.